So look at this structure. Look at this structure. What is happening? Initially, we had, y variable starting from first observation to n observation. This constant term, and there is one explanatory variable, say x21. So the
You have to present it the screen, I guess.
okay, it's very Is it visible now?
Yes, ma'am.
Yes, ma'am.
Okay. So this is the structure of a multiple linear regression model, MLRM, multiple linear regression model. We are familiar with the structure yi is equal to beta 1 plus beta 2 x2y format. In other words, we are familiar with this particular zone. We know that yi means we have observation y1, y2 to yn. We have the intercept term like this, and we have one explanatory variable, x2 say, and for that explanatory variables, we have a number of observations. The gradient coefficient is beta 2. So this particular segment we present as yi is equal to beta naught plus beta 1 x1i plus ui in this format. We consider this segment and this error. Now, in context of a multiple regression model, multiple linear regression model, we will have more explanatory variables. That is, we will not only have x21, but also we will have x31 to xk1, x32 to xk2. So first, actually, we started with, say, a demand equation where y indicates quantity demanded and x indicates price of the commodity. Now we are increasing our database, okay, increasing the features of the model. We are considering income of the consumer, we are considering price of the related goods, we are considering say geographical location, we are considering education, we are considering gender. So all these aspects are coming. Now to begin with, we are not considering any x which is qualitative in nature. That is, though I said about the gender aspect, none of the x variable actually indicating the gender aspect. All the x variables are continuous in nature. There is no x variable which is binary or qualitative in nature. When we will discuss about the dummy variable technique, we will consider some of the explanatory variables as qualitative variables. So all the x variables are continuous in nature. However, it is a change with the two variable model in the sense that we are bringing several explanatory variables in our model. So the first equation can be written as y1 is equal to beta 1 plus beta 2 x21 plus beta 3 x31 plus up to beta k x1 plus u1 in this format. In the similar way, we can write the second y observation in this format, and we can move up to nth observation. Okay, we can move like this and we can reach at nth observation. Okay. Now, if you look at the x variable, the first subscript indicates the name of the variable, say price. Therefore, it is x2. And the second subscript indicates the observation, first observation, second observation, up to n observation, first, second, up to n observation, first, second, up to n observation. Okay. And rest of the things I hope you are understanding. So it is basically yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus beta 4 x4i plus beta k xki plus ui. This kind of construct. Now, once we get this setup, because of many reasons, we have to present it, or we present it in the matrix format. As long as we talk about a two variable analysis, we may avoid the matrix formulation. In a standard way we proceed. However, when we consider this kind of a multiple linear regression model, to understand several aspects, we need to bring the matrix formulation of the entire thing. So the above equations can be presented in this format if we use the matrix algebra. Actually, all y observations can be considered in a column vector like this, y1, y2 to yn. Similarly, all u observations can be presented using a column vector like this. Okay. So I think you have pen and paper with you. So please write down or take a note on the orders of vectors and matrices. Now, what is the order of this y vector? Anyone?
N cross 1.
N cross 1. Very good. And similarly, the u vector is also n cross 1. So both y and u have the similar structure. Okay. So both of them are n by 1 vector. Now, all the x I am considering in a matrix, x21, x22 up to x2n, x31, 32 up to 3n, xk1, k2 up to kn. So all the x variables I am considering in one matrix. The first column of x matrix is given by 1 if there is an intercept in the model. Because, if you consider the product of matrices, rule of product of matrices, in that case, if you look at the first row and these beta column, what we are getting, beta 1 plus beta 2 x21 plus beta 3 x31 plus beta k xk1, this. For the second, beta 2 will be multiplied with this, for the second row, again we will start like this, beta 1 plus beta 2 x22 plus beta 3 x32. So it will move like that. Okay. So if I multiply the rows with these beta column, we will get back all these equations, all these n number of equations. Number of observations will decide what will be the number of equations here. So we have n equations here. So all these n equations can be summarized using these, matrix and vector notations. So are you understanding this matrix vector structure? Is it fine to all of you? Yes or no? Are you understanding, or should I need to repeat?
Yes, ma'am.
Yes, sir.
Okay. Now, what will be the order of these X matrix? What is the number of rows?
N.
N is the number of rows, number of equations, and what is the number of columns?
K. K.
K. Yes. Yes. So, the order of this matrix will be n by k. N by k. And what is the order of this beta vector?
K by 1.
K by 1. So x is of order n by k, beta is of order k by 1. So what will be the order of this entire product?
N cross 1. N by 1.
N cross 1. Very good. And what is the left hand side? N cross 1. So this is the combination of two n cross 1. So everything is consistent. Understanding the matter?
Yes, ma'am.
Okay. So n is the number of observations which will provide us the number of equations we are considering. K is the number of unknown parameters. So this entire thing can be summarized by this equation, capital Y is equal to x beta plus u, where Y is a vector of order n by 1, x is a matrix of order n by k, beta is a vector of order k by 1, and u is a vector of order n by 1. Okay, so this is the matrix presentation of this set of n equations with k number of parameters. Once we understand the presentation of a multiple regression model, next we have to consider the assumptions of the error term. Assumptions of the error term. Here you will find that all the assumptions you did in case of two variables, all these assumptions are retained in a multiple regression framework. All the assumptions are retained. All the assumptions are retained. There will be one more additional assumption. There will be one more additional assumption ensuring that the columns of this matrix, this X matrix, should be independent to each other. If the columns of X matrix are linearly dependent to each other, that will generate the problem of multicollinearity, linearly related to each other. Explanatory variables are linearly related to each other. If this is a context, then that is the problem of multicollinearity. Okay, we discussed about heteroscedasticity problem, we discussed about autocorrelation problem, So multicollinearity is another kind of problem which emerges from the X matrix if there is linear relation among the columns of X matrix. In other words, if X2 and X3, X2, X3, X4, or X2, X3, X4, X5, these are related to each other. Okay, so so all these things are there. So this will be a new assumption that columns of X matrix should not be related to each other. When we are talking about these relations, we will simply consider the linear relation, because so far we talked about partial correlation, simple correlation, and multiple correlation. The simple correlation that will be applicable in this context, and that can measure only the linear relationship. Okay, so linearity is our background, so we are not moving away from linearity. So when we will consider any kind of relation, association, we will confine to the linearity. So let's start with the first assumption. You are familiar with this assumption: expectation of ui is equal to 0 for all I. Expectation of ui is equal to 0 for all I. Now, when we are using the notation of vector and matrices, capital U is nothing but the error vector. So expectation of u vector is equal to a null vector. Expectation of u vector is equal to a null vector. However, this is equivalent to the assumption expectation of all ui's should be equal to 0. So it is reasonable to assume both the positive and negative discrepancies from expected values will occur, and that on balance they will average out at 0. So you learned this concept in context of a two variable analysis. Simply I am repeating that. Is there anyone who has problem with the first assumption, assumption 1?
Ma'am, capital U take U?
U vector. Just look at the last line. Y is equal to x beta plus u is the summary of the entire thing. So capital U is nothing but the entire U vector.
Acha, okay.
Stage of all observations. So next we are moving to the assumption of homoscedasticity and non-autocorrelation. Now, in case of two variable analysis, we separately talk about the variance and the covariance between the error terms. However, if I consider the concept in terms of matrix algebra, what we get is a dispersion matrix, variance covariance matrix, which is also called the dispersion matrix, DISPERSON, dispersion matrix or variance covariance matrix, where along the diagonal we will get the variances between the error terms, and along the off diagonal we will get the covariances between the error terms. Okay, so when we consider the multiple regression model, we will not separate out the assumptions as assumption 2 and 3. Rather, in assumption 2, we will cover both the assumption related to variances of the error terms and covariances of the error term. So we are moving to the assumption of homoscedasticity and non-autocorrelation, assumption 2. When I am writing var of u vector, basically I am indicating variance covariance matrix. This is the variance covariance matrix. So though I am writing value or v of u, it will give you both the variances as well as covariances. Now, how we generally write this thing? Expectation of ui minus expectation of ui whole square of that, if it is variance, and expectation of ui minus expectation of ui into uj minus expectation of uj if it is covariance. Now, in context of matrix algebra, we present the thing as expectation of u minus expectation of u, that part you know, multiplied with u minus expectation of u transpose, u minus expectation of u into u minus expectation of u transpose. You know, if you have pen and paper, here, if you like, you can take note of several facts. Now, what is the order of u vector? What is the order? Just you mentioned what is the order of
N cross 1.
N by 1. Very good. So, what will be the order of u minus expectation of u? If u is of order n by 1, what will be the order of expectation of u?
N cross 1.
What is the answer? Would you please answer that?
N cross 1.
देखो, expectation of u is a single value, isn't it? It's the mean.
Yes. Yes, ma'am. Yes.
So it is the mean. When you are considering u minus expectation of u, what you are doing? Suppose mean is 5 and your u value is 1 to 10. So what you are doing? 1 minus 5, 2 minus 5, 3 minus 5, 4 minus 5. So you are doing the thing in this way. So what will be the final order of u minus expectation of u? If u is of order n by 1 and if expectation of u is a constant, what will be the order of u minus expectation of u? Bolo.
Remains N by 1.
N by 1. Very good. Order will be n by 1. I have n observations, and from all the observations, you know, or I have 10 error terms. From all the 10 error terms, I am subtracting its mean. So I am getting back the similar kind of column. Nothing else. If I have this column at every level, I'll consider minus of mean, minus of mean, minus of mean. However, my order of the vector will remain unchanged. Everybody, are you agreeing with the matter?
Ma'am,
Yes.
so if we take expectation of that capital U matrix, so we'll get a n cross 1 column vector with each value equal to 0, right?
ওভাবে কেন ভাববো? Expectation of u is a constant. তোমার nটা observation আছে u এর, and you will be able to calculate expectation of u. আচ্ছা, তুমি বলছো জিরোর জন্য, মানে বাই দ্য ফার্স্ট অ্যাজাম্পশন জিরোটা ইমপ্লিমেন্ট করে বলছো?
Yes, ma'am.
আচ্ছা,
যদি assume করি expectation
সেটাই
UI গুলো,
আমি আসছি। আগে অর্ডারটা বুঝতে পেরেছো কিনা বলো?
yes ma'am, ওটা বুঝেছি।
সেটা যদি নাও হতো তাহলেও তো অর্ডারটা একই থাকতো। যদি এক্সপেকটেশন অফ ইউআই ইজ সাম কনস্ট্যান্ট, এখানে না হয় অ্যাজাম্পশন দিয়ে জিরো, যদি জিরো না হয় কনস্ট্যান্ট হতো, তাহলে কি অর্ডারটা বদলাতো?
নো ম্যাম, মানে ভ্যালুটা হয়তো বদলাতো, বাট অর্ডারটা বদলাতো না।
Order বদলাতো না। That is the main thing. Your order, now I am talking about the order. So u minus expectation of u will have the same order as u. So এই যে ডিফারেন্সটা, order of this difference is n by 1. So please note down that n by 1, u minus expectation of u is of order n by 1. Today I do not have the DG board, therefore parallelly I'll be not able to write the thing in the pen box. So please note down the order of this is n by 1. Now what will be the order of u minus expectation of u transpose?
1 cross n.
1 cross n. So what will be the order of this entire thing?
N cross n.
N cross n. So we are starting with a vector. However, we are generating a variance covariance matrix of order n by n. So it will give us, u minus expectation of u multiplied with u minus expectation of u transpose will generate a matrix of variance covariance matrix, which will be a symmetric matrix of order n by n. So please note down this fact. Now, what Aratrik, started to tell us, I'll just repeat that thing. Expectation of u is equal to 0 by the first assumption. Expectation of u is equal to 0. So if I put 0 in both the cases, we are getting expectation of u prime. Expectation of u prime. So this entire thing reduces to expectation of u prime. Okay, expectation of u prime. Order will remain n by n. Now, if I consider u prime, u is of order n by 1. U prime is of order 1 by n. So please, in your copy, write down the u vector, and then you write down the u prime vector, take product of these two, and check whether you can generate this kind of matrix or not. So you take a column vector u1, u2 to un, multiply this with a row vector u1, u2 to un, a column vector u1, u2 to un, that you multiply with a row vector u1, u2 to un, and please tell me whether you are getting these values or not. I'll request everyone to do this. You are familiar with matrix multiplication. It's not new to you. Here we are applying those tools. That's all.
Yes, ma'am, we
Ma'am,
obtained this matrix.
You obtain this matrix. Lakshadweep,
ma'am, একটা question আছে।
তো Lakshadweep পাচ্ছ এরকম matrix?
ম্যাম করছি।
হুম।
ম্যাম
Yes.
ম্যাম বলছিলাম যে এই যে ম্যাট্রিক্সটা পাবো এক্সপেকটেশনটা নিয়ে, এটার ডায়াগোনাল গুলো ভ্যারিয়েন্স আর বাকিগুলো কোভ্যারিয়েন্স বলে ওটাকে।
যাইনি, আগে করিনি সবাই, আমি তো ওটা
ম্যাম
বলিনি।
ওটা ভ্যারিয়েন্স কোভ্যারিয়েন্স ম্যাট্রিক্সটা কেন বলে তার কারণ ওটাই তো মানে
হ্যাঁ।
এটা। আচ্ছা
বাকিরা এরকম পাওয়া যাচ্ছে?
Yes, miss.
আচ্ছা, অর্ক করছো এরকম, সলভ করছো?
হ্যাঁ ম্যাম পেয়েছি।
আচ্ছা, so once we get these products, as Dorpok is mentioning, in the next step we will take expectation of all the components. Expectation is here, so we will take expectations of all the components. Now if you take expectation of components which are in the diagonal, you are getting expectation of ui square, expectation of u1 square, u2 square, etc. We assume, and all this expectation of ui square is nothing but the variance of ui. It is nothing but the variance of ui. Okay, we assume these variances are constant. That is, for expectation of u1 square, that is sigma u square, expectation of u2 square, that is sigma u square, expectation of un square, that is also sigma u square. So I consider the variances are all constant. This is nothing but the assumption of homoscedasticity. Already you are familiar with the idea of heteroscedasticity. If we consider heteroscedasticity, variance of u1 square will be different from that of variance of u2 square, that will be different from variance of un square. That is the idea of heteroscedasticity. However, I'm not considering that. I'm assuming that variance of u1 square is equal to variance of u2 square is equal to variance of un square, and these variances are nothing but sigma u square. So this is the assumption of homoscedasticity. Simultaneously, I'm also assuming expectation of ui uj, that is expectation of rest of the terms we have apart from the diagonal terms. All these terms are equal to 0. Expectation of u1 u2, expectation of u1 un, expectation of u1 u3, expectation of u2 u3, every term, that is all expectation of ui uj is equal to 0. So that I am assuming. So what if I operate expectation, then what I am getting? I am getting a matrix where I have sigma u square in the diagonal, sigma u square in the diagonal, and all of diagonal terms will be nothing but 0. All of diagonal terms will be nothing but equal to 0. So what we can do, we can take sigma u square common. So if I take sigma u square common, I have 1, 1, 1, 1, 1 in the diagonal, and all of diagonal terms are nothing but equal to 0. So I'm getting identity matrix of order n by n. So if I take sigma, first I have to take expectation. There I am making double assumption of homoscedasticity and non-autocorrelation. The assumption of homoscedasticity and non-autocorrelation generates a matrix where we have sigma u square in the diagonal and all of diagonal terms are equal to 0. In the next step, when we consider sigma u square common, if I take sigma u square common, I will get one identity matrix with sigma u square. And that identity matrix is of order n by n, which we can present as IN, identity of order n, which means it is a symmetric matrix of order n by n. So this is giving us, or this is telling us about the double assumption, homoscedasticity, and non-autocorrelation. If we write value, that is variance covariance of error vector is equal to sigma square I, this is indicating the double assumption of homoscedasticity and non-autocorrelation. Anyone, any question?
ম্যাম কোনটা সিমেট্রিক ম্যাট্রিক্স বলেন, সিগমা স্কোয়ার আইএনটা?
আইএনটা সিগমা ইউ স্কোয়ারটা একটা কনস্ট্যান্ট, বাইরে বের
ও
করে এনে আইডেন্টিটি ম্যাট্রিক্সটা, আই যে ম্যাট্রিক্সটা সেটা অফ অর্ডার n বাই n। তোমার পুরো ভ্যাক্টরের ম্যাট্রিক্সটাই তো সিমেট্রিক, দিস ইজ অফ অর্ডার n বাই n, তাই না?
হ্যাঁ হ্যাঁ।
So please take note of the fact that this is a symmetric matrix of order n by n. The variance covariance matrix is a symmetric matrix of order n by n. So when I took the product, actually we generate a matrix of order n by n. Okay. Now alternatively, if I consider the product u minus expectation of u transpose with u minus expectation of u, what will be the order? Suppose instead of doing this, I consider this transpose minus this, that is the row multiplied with column. So what will be the order of that?
1 cross 1.
1 cross 1. So 1 cross 1 is a scalar, isn't it? It is a scalar. So actually, in that case, I'll get summation ui. If I multiply the row with the column, I'll get, summation ui. So that will be a scalar. Not summation ui, actually ui square, first I'll, summation ui square, rather, summation ui square. So that will be a scalar. So later in a multiple regression analysis, when we will define residual and we will like to find out residual sum of squares, we will do exactly that thing. We will consider the row vector of the residual and multiply with the column vector so that we will get summation ei square. The RSS, residual sum of squares, will be generated in this way. So while we are applying matrix algebra, you should be very careful about, whether you are multiplying a vector with another vector, what kind of ordering you need, whether from the vectors you need to generate matrices or you need to generate a scalar component, So your style of multiplication will be, differ. If you want a scalar, if you want a matrix, if you want a vector, so all these points are there. It's very interesting. However, you need to keep this point in your mind that what I need, whether I need a scalar, whether I need a matrix, whether I need a vector. So your operations will be like that. However, that is not important while I am discussing the assumption just I mentioned, It is not related to the idea of homoscedasticity and non-autocorrelation. Third assumption here is similar to that of the two variable analysis case. We considered covariance between x and error that will be absolutely equal to 0 to maintain the linearity of the model. So similar assumption will be retained in context of a multiple regression model. So data matrix X, which is of order n by k, is non-stochastic. We consider this to be non-stochastic. This means In repeated sampling, the values of x's are held constant. We consider this. This assumption is sufficient to guarantee stochastic independence between x and u. Okay. In other words, we assume covariance between the x matrix and u vector that is absolutely equal to 0. Okay. So nothing new here. We are considering the covariance between x and u is equal to 0. If we consider x to be non-stochastic, this condition will be trivially satisfied because u is always random. Okay. However, we can put note in this context that non-stochasticity of x is not necessary. X may be stochastic. In that case also, it may be independent of u. Conventionally, to address the things simply, generally we consider x to be non-stochastic, so that always you will have independence between x and u. So I hope this assumption is fine to all of you. So all these assumptions, expectation of ui is equal to 0, variance, covariance, giving the homoscedasticity, non-autocorrelation. Third is covariance between x and u is equal to 0. Everything is fine up to this. Anyone, any question up to this? Okay, so I'm proceeding further. So this assumption is a new assumption. Now the assumption I'll talk about, this is a new assumption. This assumption was not required in context of two variable analysis because there was no chance that columns will be linearly dependent. Only when you are considering a number of explanatory variables or more than one explanatory variables, in that case only there is a chance that you can have, or we can construct this kind of assumption. Okay. So this assumption was not there in context of a two variable analysis. This assumption we are incorporating once we are moving towards the multiple regression model. Okay. Now what we require is that columns of X matrix, columns of X matrix. This is the X matrix. Columns of X matrix should be linearly independent to each other. Okay. Now, what are the columns? Columns are nothing but observations on a particular explanatory variable. So if X2 is the price of the commodity, it is different observations on price of the commodity. If X3 is income of the individual, then it will indicate n observations on income. If it is, the height of individual, it is, the column for the heights of all the observations we are considering in our analysis. So it is like that. To begin with, we are assuming that there is full independence between price and income, full independence between price and height, no relation between income and height. So all these things. Okay. There is no linear dependence among the X variables. Look, one of the major assumptions in a classical model, X and U should be independent to each other. Otherwise, linearity aspect will be disturbed. That is, whatever components we have in the right-hand side of the regression model, we need independence among these. Now, the difference between a simple model, that is a two-variable model, and a multiple regression is here we have more explanatory variables, So if I need the independence between X and U to maintain the linearity, I hope you are understanding, we also need independence between two X's. Okay, we need independence between all x columns. Otherwise, we will be not able to maintain the linearity structure. It is multiple linear regression. So if x2 and x3 are functionally related, or x2 and x4 are functionally related, in that case, we will be not able to maintain the linearity of the structure. So for the same reason, we need that all x columns should be independent to each other. All x columns should be independent to each other. Now, I'll bring the notion of rank of matrix. Rank of matrix. Rank is minimum of independent row or column. Rank of a matrix means minimum of independent row or column. If I consider a particular matrix where we have 5 independent rows and these 5 is less than the value 8, say I have 8 independent columns, in that case rank will be 5. Alternatively, if I have a matrix where we have 6 independent columns, however 9 independent rows, in that case rank of the matrix will be 6. So it is minimum of independent rows or columns. So here, the independence between all x's will be presented by the statement that X matrix has full column rank. X matrix has full column rank. That is, rank of this X matrix is equal to K. Rank of this matrix is equal to K. Okay, there are K independent columns in it. So rank of the matrix is equal to K. Simultaneously, we will mention that number of rows, that is n, should be greater than k. N should be greater than k because degrees of freedom of the model is given by n minus k. So if n is not greater than k, we will not have sufficient degrees of freedom. Okay. So in context of a regression model, number of columns that should be lesser than number of rows. And all the columns will be independent to each other. So if I calculate minimum of independent rows or columns, in that case, naturally, the number of columns that should appear as the rank of the matrix, because we have to maintain the degrees of freedom. So n should be always greater than k. So if n is always greater than k, the rank condition will be provided by the columns. And here we are considering all the columns are independent. So rank of x will be given by k. In other words, we can say that X matrix has full column rank. The assumption is X matrix has full column rank. This indicates two things. Number one, it indicates all the columns in the X matrix are independent. Number two, it indicates number of rows is greater than K. N is greater than K, maintaining the sufficient degrees of freedom. So let's have a look at the assumption. Since the regression equation has a linear structure, while producing the the included causes, while producing the effect, there will be a comma. The included causes, effect means y, the included causes should not interact among themselves. Included causes means included explanatory variables should not interact among themselves. This implies the columns of matrix X should be linearly independent. This implies they should not interact. This implies the columns of X matrix should be linearly independent. So rank of X will be equal to K. Rank of X is equal to K. Now, rank is minimum of independent row or column. So in what logic I'm selecting K, not N. The logic is the second one. This K should be less than N. This K should be less than N because we need to maintain the sufficient degrees of freedom of the model, and degrees of freedom in a K variable model is defined as N minus K. Degrees of freedom is defined as N minus K. So since it is a new assumption, if anyone have any query, any question, or could not take note of certain facts, in that case, please tell me, I'll repeat the things.
ম্যাম বলছিলাম যে রো গুলো ইন্ডিপেন্ডেন্ট, মানে এরকম কিছু আছে? যেহেতু আমি
থাকতে পারে, ইন্ডিপেন্ডেন্ট থাকতে পারে, ডিপেন্ডেন্ট থাকতে পারে, সব রকম থাকতে পারে, মিলিয়ে মিশিয়ে।
এনটা যেহেতু গ্রেটার দেন কে, তাহলে ওটা র্যাঙ্কটা কে হবে? তার জন্য তো রো গুলোকে ইন্ডিপেন্ডেন্ট হতে হবে, সেটাই বলছি।
যদি n should be sufficiently large than k, তাই না? ধরো তো হতে পারে দুটো রোর মধ্যে একটা কিছু ডিপেন্ডেন্সি তুমি পেলে, that will not disturb the scenario. This assumption should be maintained. Okay, n should be strictly greater than k, very, very greater than k, because you should have sufficient degrees of freedom in the model. Number of observations will be 2 lakhs, 3 lakhs, if not 10 lakhs, it will be in thousands, in lakhs. Whereas the number of explanatory variables and therefore the number of parameters in the model, that will be, 10, 15, 20. How many explanatory variables you will be able to consider? However, number of observation will be too large. Okay, so if this is the context, so what you need, that you need to maintain a sufficient gap between n and k. That's all. Okay, you got the answer to your question?
Yes, ma'am.
Anyone else? Any other question? Okay, so this is a new assumption. Please take care of this new assumption, what it indicates, etc. Because this particular assumption, if this particular assumption is not maintained, that will generate the multicollinearity problem. That will, if this particular assumption is not maintained, that is X matrix does not have full column rank, in that case, it will indicate the linear relationship between the X columns. And if there is linear relationship between X columns, that will be the problem of multicollinearity. Like heteroscedasticity, autocorrelation, multicollinearity again will disturb some of the characteristics of the regression coefficients, and for that matter, we need to rectify it, and we need to suggest what will be the mechanism of estimation to get best linear unbiased estimator. So all these things are there. So, this assumption is very, very important.
ম্যাম,
Yes.
তার মানে আপনি কি এটা বলতে চাইলেন যে এনখানা রো আছে, তার মধ্যে যদি কটা ডিপেন্ডেন্ট থাকে, তাহলে বাকি এন মাইনাস যতগুলো ইন্ডিপেন্ডেন্ট রো আছে সেটাও কে থেকে বড় হবে নাম্বার অফ ইন্ডিপেন্ডেন্ট কলামের থেকে?
অনেক বড়। তা না হলে তো তোমার ডিগ্রিস অফ ফ্রিডম থাকবে না।
আচ্ছা,
আমি তোমাকে একটা এক্সাম্পল দিলাম না, আমরা যা রিসার্চ লেভেলে একটা অবজারভেশনের সেট হয় 10,000-এর উপরে, তার থেকে ছোট অবজারভেশন সেট হয় না, বুঝেছো? তাহলে একটা রিপ্রেজেন্টেটিভ হবে না, পপুলেশনের সব সাইজ দেখো তো ঠিক, সেখানে তুমি যদি 10,000 স্যাম্পলও না নাও, তাহলে তো রিপ্রেজেন্টেটিভ হয় না, তাই না?
Yes.
প্রাইমারি সার্ভে করে খুব স্পেশাল টপিক স্পেশাল জোনের উপর ফোকাস করে কাজ করলে 1000-5 স্যাম্পল তোলা হয়, বাদ বাকি তো সবসময় বিশাল স্যাম্পল সাইজ হতে হবে না, আদারওয়াইজ দ্য স্যাম্পল উইল নট বি রিপ্রেজেন্টেটিভ। তোমার সংখ্যা হচ্ছে মানুষের তো মানে বিশাল, তাহলে তার সঙ্গে রিপ্রেজেন্টেটিভ কিছু করা মানে ইউ হ্যাভ টু টেক আ ভেরি লার্জ স্যাম্পল, otherwise how the things will be represented. So there will be a huge gap between the number of observations we consider and the number of parameters we estimate. Okay. Actually, nothing is specified regarding the linear independence of the rows. Okay. Here the matrix should have sufficient, here the matrix should have number one, full column rank, number two, these k values should be smaller, strictly smaller than n. That's the idea. Okay. And the next assumption is regarding the distributional aspect of the error vector. The U vector has a multivariate normal distribution. In case of two variable analysis, we consider independent and identically distributed with normal, with expectation of ui is equal to 0 and variance is equal to sigma square. Here the same assumption is maintained. However, it is a multivariate normal distribution. Expectation of ui is equal to 0. However, in place of variance, we will write sigma square in, the entire variance covariance matrix. So it is a multivariate normal distribution. Finally, it is again a conditional mean modeling. The yi values we are trying to find out, that is actually the values given xi. So the values are related to expectation of yi given xi. So again, we are going for the conditional mean modeling, and for that matter, we should not have outliers. We assume that there is no large outliers. Otherwise, the entire estimation, etc., that will be erroneous, because that will disturb the mean. And for that matter, the result you are reporting, that is not the true picture of the scenario. So these are the assumptions. These are the assumptions related to the k variable model. You have to just learn these assumptions. This assumption is new. Rest of the assumptions were there in the two variable analysis. Only the style of presentation is changing under certain context, especially in context of homoscedasticity and non-autocorrelation, because now we are using the matrix algebra. So this much only you need to practice. I think it will be better if I stop with the assumptions, because I don't want to, elaborate several things, because we have to understand the matters briefly. So these are the assumptions. With these assumptions, in the next step, what we do, we will go for estimation. We will go for estimation. Okay. Now, for the estimation, there will be no change in the technique. We will apply the ordinary least square technique. What we need to learn, how to frame the residual sum of squares. Already I mentioned, however, specifically, I need to mention how we are getting the residual sum of squares in this case. That is the summation ei square, how I'll get it. Okay. And once we get it, how, given the matrix formulation, I'll differentiate to get the values of all betas, how we will get the beta hat values, how we will get the beta hat values. So this, derivations with respect to the matrix, etc., we need to learn. That I'll do in the next class. So again, if anyone have any question on the assumptions.